UNC Chapel Hill's energy services are very important to the preservation, safety, and health of the buildings, students, faculty, and research facilities on campus. Even though it's invisible, it is the backbone of the university. Energy services at UNC include the following systems: chilled water, steam, electric distribution, and water. Each system is intertwined and they operate as one in order to reach optimal efficiency. The chilled water system is one of the most complex and sophisticated networks at UNC Chapel Hill. Its primary function is to cool buildings and equipment all around campus by making cold water through the transfer of heat. Chilled water is provided through a system of underground pipes, chilled water plants scattered around campus, and standalone chillers dedicated to individual buildings. There are five main plants at the university. The chilled water system in total has 27 miles of underground piping and cools 100 to 150 buildings. There are many people associated with UNC's energy services and chilled water systems. Examples include Lee Baker, who is the chilled water systems manager, and Lou Kellogg, who is the executive director of energy services. The Tompkins Chilled Water Operations Center is one of the 5 chilled water plants located at UNC Chapel Hill, and it opened in 2005. The plant specifically was named after Gary Tompkins, a mechanical engineer who used to work for UNC Energy Services. There are many pieces of equipment that are used throughout the chilled water process, which include the chiller, the compressor, the condenser, the evaporator, the expansion valve, and the cooling tower. The chiller appears in both the chilled water loop and the refrigerant cycle. It makes the chilled water cold, is located behind a large yellow container and holds an electric motor, which drives the creation of the cold water. Also, the cooling tower is found in the condenser water loop. The condenser water is brought up through a pipe and travels up to the top of the tower, and it spills down through the fill. As water trickles down, some of it evaporates, and that's how a cooling effect is created. Non-evaporated water trickles through the cooling tower and turns back down into the main room, which holds the chiller. The whole process of the chilled water system is a movement of heat. Heat is taken from the buildings on campus and put into the chilled water. That heated up chilled water is brought back to the chilled water plant, and a transfer of heat takes place between the returned chilled water and the refrigerant in the evaporator in the chiller. From there, another transfer of heat takes place between the refrigerant and the condenser water found in the condenser in the chiller. The newly heated condenser water is taken up to the cooling tower and is sent out into the air through evaporation. There are 3 main loops that happen in the chilled water process: the chilled water loop, the refrigerant cycle, and the condenser water loop. The chilled water loop is a closed loop taking place between the buildings and the evaporators found inside the chillers, and it consists of potable water. In the beginning of the chilled water process, chilled water supply is sent out to the buildings scattered throughout campus. The buildings heat up the chilled water, and that newly heated chilled water returns back into the evaporators. The refrigerant cycle is taking place within the chiller itself, and it is a closed loop system. The refrigerant, a chemical, starts out in the evaporator and then makes its way to the compressor. When in the compressor, it moves to the condenser, and finally into the expansion valve. The condenser water loop is an open loop system taking place between the condenser in the chillers and the cooling tower. Heat is transferred into the atmosphere, which means it has left the cycle, and the cycle contains non-potable water. The condenser water found inside the chiller cools down the newly heated refrigerant. The newly heated condenser water travels up to the cooling tower. Once there, airflow and evaporation cool down the condenser water, and this newly cooled condenser water returns back to the chiller. Within these massive chilled water plants located on campus, a complex and color-coordinated piping system exists. Certain colored pipes perform different tasks. Color examples include blue, green, red, purple, and black. Also, the darker the colored pipe is, the colder the chilled water is. A few other examples of specific equipment include a flow meter, which separates the flow of water into different pathways to create differential pressures. A flow valve blocks or allows the flow of water. It is naturally closed in case the electricity goes out in a plant. A resistance temperature detector, or an RTD, is used to quantify the resistance that water has to heat. It measures the temperature of the water using a platinum rod. Variable frequency drives, or VFDs, can be put on anything that has an electric motor. People put these devices on electric motors to slow down certain pieces of equipment. Each chiller plant on campus has access to its own programming. 2 types of signals exist: analog and digital. Each plant has 2 of each. An analog signal is a continuous signal, while a digital signal represents data as a sequence of discrete values. Each plant has a DCS system, or a cabinet with all the wires and transformers that exist at a plant. There are a few thousand lines of code for the DCS system. Finally, SCADA, or a supervising control and data acquisition, is at the core of the programming that exists in all 5 chiller plants on campus. At Tompkins Chilled Water Operations Center, there's a main control room that monitors all the chilled water plants and operations on and off campus. Within each building on campus, numerous aspects are monitored: temperature, travel, and pressure. Also, different types of signals are monitored across all 5 chilled water plants. Currently, the North Chiller plant is going through a controls upgrade. Each plant has gone through this process, and in total, the updating process has taken over 4 years to complete. Each plant took as long as the winter season to go through this process. Nathan Hefner is currently working on this upgrade process. The water storage tank is just like a battery. Cold water is put into it at night, and it is discharged during the day. From an energy efficiency standpoint, people can make the compressor do a minimum amount of work. There are three energy models that can be used to decrease the speed of the fan, which in turn leads to a decrease in power and electricity costs. Nalco Water is the world's leading provider of water treatment and process improvements. They only use fresh water when it comes to their technology and services. Water treatment is of major importance in chilled water plants. Failure to maintain a cooling water system can lead to fouling, microbiological activity, corrosion, and scaling. These four problems can lead to an increase in energy usage, damage of assets, an increase in downtime, and a decrease in product quality. The budget of the chilled water services at UNC Chapel Hill is $25 million. The three major utilities at UNC include steam, electricity, and water. The single largest user of electricity is chilled water services. They have about $140 million in operating expenses. 20% of costs they cannot control, and 20% they can control. 10% is labor, and 7% is maintenance. In the future, Kellogg worries about finding alternatives to coal because choices are very limited. Also, due to air permits put in place on campus, certain pieces of equipment cannot be run while other pieces of equipment are also running. Finally, age is another problem. About 25 to 30% of Kellogg staff can retire with full benefits right now. In 5 years, it'll be 50%. UNC Chapel Hill's commitment to water and energy include the following: commitment to water stewardship, reclaim usage, and decrease in potable water usage. UNC is over 70% efficient. It produces more than they need because they have a cogeneration plant, which means they generate both electricity and steam. UNC Chapel Hill Energy Services plays a major part in the upkeep, preservation, and safety of campus. Examples include life safety aspects, maintaining the humidity in library collections, and keeping antique musical instruments at particular temperatures and humidities. Without chilled water, none of these aspects would be maintained, and the campus would not be able to operate. Thankfully, chilled water systems at UNC Chapel Hill are able to provide the necessities that everyone on campus needs to maintain a comfortable lifestyle.